Hello, everyone. Welcome to today's Sujati Labs Tech Talk on democratizing enterprise innovation with AI and ML. We have with us our speakers, Sergio, who is the director in the innovation group in the US and is the Sujati Labs USA lead driving Thinkubator Business GTM. Ram is the Sujati USA chief technology officer with over 20 years of experience in defining technology strategy and managing large scale digital transformational programs across industries. Vijay is the Symphony AI CTO. He is the technology leader and an entrepreneur with extensive experience leading technology teams in companies ranging from startups to Fortune 100. Eric is Symphony AI's Vice President of Customer Service. He leads technical sales and support across Symphony AI solution, focusing on the public sector. Over to you all to tell us more about this topic.
All right, thank you, Ishmeet, and thank you to our guests for joining us today to talk about this topic, democratizing innovation with AI and machine learning. Also, thank you for joining us to take in this information. I hope you find it useful and be able to, apply it for your customers, your clients, and projects. This is the agenda we have for today. We're going to do a quick just sort of overview of the mega trends that are involved with related to data-driven innovation and some of the challenges and some of the new approaches that we're going to be presenting today that we think that will be very effective in terms of how you can achieve, innovative product service design in the enterprise. And specifically, we'll be covering just an overview of the AI ML framework for deep design in Thinkubator Business, which you'll see provides insights and guidance on how to accelerate and deliver innovative products and services. And then we'll have SymphonyAI provide an overview of their enterprise AI platform, which enables a lot of the things that we'll be talking about in terms of the framework. And we'll see some really innovative capabilities that SymphonyAI has in their platform that I think you will find really, really compelling and useful as you seek to accelerate and apply data-driven innovation. And then we'll get into some demos. Eric will guide us through that, and we'll get to see the platform in action. And then we'll have Q&A. But as Ishmeet said, this will be interactive. So if you have any questions along the way, feel free to chime in. So just to kind of begin the quick megatrend overview, I think what we're seeing a lot of is that the CXO suites are running into many challenges in fast-paced environments where, I think the quick reaction is to just hoard as much information as you possibly can and have that information be available so that some value can be extracted at some point in time. But I think a lot of enterprises have a serious challenge in understanding how to do that effectively, and then moreover, how to do that with speed and velocity. And I think there are other challenges too in terms of the pressure to innovate and to make more innovative products and services to keep ahead of the competition. And I think that data is a key factor in being able to produce these types of innovations where you're not just getting incremental improvements, but be able to even introduce disruptive products and services into the market. So I think that this is introducing a new dynamic within the enterprise where many businesses are realizing that you just really cannot approach this sort of situation with sort of a keeping the lights on type of mentality. So I think that businesses are beginning to see that there's another type of mindset that is needed to help address these challenges in terms of being able to be more creative and then also be able to enable more exploration faster so that the creative teams can be able to arrive at these concepts much faster and to help kind of build out an innovation ecosystem, which includes data data sources and varieties, different types of varieties of data, incorporate that into the value creation. And so this brings us to the mindset that's involved, right? Where we're going from a strictly analytical mindset, where we're more focused on feature sets, where we're looking at more in terms of the overall impact, what's the overall experience that we're trying to deliver to create these disruptive products and services. And oftentimes, in the past, there was a heavy focus on just manufacturing and being able to just put more features into the product. But now, I think there's a more sort of holistic view as to what a product or service really is. So I think that this mindset helps to approach that, sort of the creative, connecting the dots, if you will, of designing and also deploying these types of products and services. So we've introduced design thinking into Thinkubator Business, and this is a key sort of component that drives the creative, flow to arrive at innovative products and services. But I think we're also, introducing as a part of the platform is that in combination with design thinking, we're also enabling that flow with machine learning and AI. So we talk about this concept of deep design, and what that means is you're able to dive really deep into the data really fast. And when we say deep, it's about very hidden underlying patterns, but also vertical sector type of data. For example, you might have healthcare or retail or manufacturing, where you're able to make sense of that data and make meaning of that data that is applicable to that particular sector or problem space. So you can get to those insights much faster. And what the result is, you end up with a much more compelling product and services that really drive value for your markets and customers. And so here's kind of an overview of the Thinkubator platform. As you can see here, we have the AI ML framework for deep design, which we kind of show in context of the flow of how it interacts with the design thinking flow. So as you are sort of beginning to look at a concept and doing some initial sort of immersion and research, and then you're just trying to arrive at a point of view where you're trying to define what the concept is, and this is where you sort of you get the framework to help you get those insights so you can develop that point of view, which is really key before you get to the ideation stage, because that your point of view is your sort of your launch pad into ideation, because it helps you to get started on the right track. Make sure you're actually addressing the concept with the biggest opportunity to deliver value when you get downstream. And this is just quickly just showing kind of a reference architecture as part of the framework. You'll see this pattern in many machine learning systems across sectors. You can apply this pattern in energy, in retail, healthcare. So you can see the different sort of overall phases and the components that are involved. And this just kind of gives you a picture of what a sort of a machine learning architecture would look like, and the different components and services that would enable at the end. At the end of this, what you want to deliver is those insights, whether it be whether it be mobile or desktop visualizations, and also different kinds of audiences, whether it be business users or data scientists that can begin using this data to develop those insights for data-driven innovation. And we also just provide some baseline guidance on how to design and evaluate machine learning models, including algorithm selection, data pipeline to prepare data for machine learning experiments, some guidance around feature selection, and then also just the overall sort of like training and evaluation of models to arrive at the optimal model for your particular sort of problem that you're trying to enable. And so some of the classes of products and services that I just put this in here to sort of provide sort of a kind of some examples or inspiration for some of the product and services that you can consider or think about. We think about the age of intelligent products and services, and you have flood of data coming in, not just from software but from IoT sensors, from in the open world, from really any place you can imagine, being able to consume that data and be able to drive innovative experiences specifically around like new services, and then also context-based products and services where you sort of collect and sort of make sense of the world around the product or service. They can and drive some value for customers. Then of course there's also the learning class where you have some kind of intelligent device that can learn from its environment and can actually deliver some sort of new experiences or capabilities that would not be possible otherwise. And this just shows some specific examples where you can actually enable new revenue streams from these kind of services. And then also new, in terms of the context of how you can enable intelligent products, smart products that can not only just perform a given function in the physical world, but also have contextual data that's being fed into the machine learning AI system, where you can enable new capabilities and features in applications downstream. And then of course you have the learning types of products, and I think the biggest example was Nest device, where it can actually learn from its environment and then also sort of predict what the future space would look like and what the future conditions would look like, so you can deliver a new experience for the persons that have the Nest
So we
product.
have a question.
Oh yes,
Have you come across a few use cases?
I think I lost you, Mr. Mead. Can you please repeat that? I think I lost your audio.
I think it is one of the questions that has been asked on the chat. Have you come across any use case for ML AI applied in green tech?
Oh, absolutely. Yes, definitely. That's a great question. And yeah, definitely, I think sustainability is a huge use case that actually applies across sectors. So you can imagine if you have, like, for example, a supply chain, and you want to find opportunities to reduce carbon emissions across the supply chain, you can definitely, start gathering data and begin to understand where the opportunities are. And I think using AI ML, you can definitely arrive at a much cleaner supply chain where you reduce carbon emissions. And that's actually is a big focus of Sogeti Labs as well right now. So I'm expecting that you'll be hearing more about that specific use case in the future. But great question. Yeah, so I want to get into some specifics here now. We kind of looked at the megatrends, the kind of a quick reference architecture overview. So now I want to talk about some enablement in the framework. And so we have our partner here, SymphonyAI, and we actually met them through our Applied Innovation Exchange program out in San Francisco. And we definitely found their technology platform compelling to the use cases that we've been looking at in terms of innovative design for products and services. And so just a quick kind of feature highlight. One of the features that we found so compelling and so novel in terms of, and so different of how they approach developing these accelerated insights is something called topological data analysis. And that's sort of a kind of visual way to make sense of the data. And you'll see more of that in the demos firsthand, so you can have a look for yourself. And so the whole idea is that this platform not only makes it faster to arrive at those to those deep insights, through TDA, but it also makes this capability available to like business users, where you can put this in front of users that have some product service responsibility to drive either like sort of like product concept development, product management, and go to market for that particular in a business, and being able to make this available to them so that they can be part of the innovation pipeline. Something I like to call real-time innovation, where you have these pipelines that that are operating in the enterprise in real time. We kind of get away from this concept of a lab that happens inside four walls. These are like real-time innovation pipelines that are enabled and powered by business users that can drive innovation and drive these insights to create these awesome products and services. So we'll see that in this presentation from SymphonyAI. And with that, I'd like to go ahead and turn it over to Vijay, SymphonyAI CTO, to provide kind of an introduction and overview of SymphonyAI.
Great. Thanks, Sergio. And hi, everyone. It's great to be here, and I'm looking forward to having a conversation. So as I and Eric go through the next several minutes of some slides and demos, please feel free to chime in and ask any questions you have. So just a few words about who we are. So we are an enterprise AI company, and our focus is to apply AI and ML to solve specific problems in different verticals and businesses that we play in. And our focus is very much on driving value in the different verticals. So we'll talk a little more about that in the coming slides. Next slide, please. So when we think about where we play, we are in all of these verticals that are listed here, and the bylines give you an idea about the types of applications that we power for different customers across retail, CPG, public sector, enterprise services, media, financial risk, and crime, and then industrial as well. And as we go through our journey, our focus is very much on figuring out the right applications to apply data, AI, ML, and the insights that we get from applying these techniques. But it's all grounded in our deep knowledge and vertical expertise. And beyond just the application of AI to say, well, okay, here's what we predict is going to happen. Our focus is on helping our customers not only know what's going to happen, but also help contextualize it through explainability, and then be able to take recommended actions as a result. So that is the focus of the company, and we are very much focused on enabling both data scientists and citizen data scientists as we go through our journey with the focus on different verticals. Next slide, please. So when we think about what we are doing, I touched on our vertical focus and expertise. So we have very deep expertise in all of these verticals that I just mentioned in the previous slide. So it starts with the vertical expertise and then is grounded in the data and the domain-specific data and the data models that we have built for each of these domains. And then that then translates into our ML models that solve specific problems in these domains as opposed to generic, let's say, clustering algorithms. That all of this is built on really rich and powerful AI platform that I'll touch on as well, all of which helps both data scientists and citizen data scientists to go from data exploration to inference in a really efficient way. And that is the focus of the platform. And all of what we are doing is built for cloud, is cloud native, and is built for massive scale as well. We have uh, some of the largest grocers in the world who are customers, to uh, some of the largest financial institutions, to industrial facilities that use our products. So by definition, we've had to build our products for massive scale. Next slide, please. So when we think about the journey of the platform that enables all of this work, we started our journey with the platform that we call EurekaAI. And the version 3.0 of the platform, which was the previous version, was very much grounded in the topological data analysis algorithm that Sergio just mentioned. And Eric is going to go through the demo, and I think you'll find that super interesting to see how we use the power of TDA to do unsupervised learning and data exploration. TDA came out of some researchers at Stanford. It's grounded in deep math. It harnesses really the power of different nodes, the distance between nodes, and the characteristics of the data to find interesting clusters that most normal clustering algorithms don't. So I think of this as a really powerful tool for your initial data exploration and figuring out where you focus the data. And TDA works really, really well for those types of applications. And we've used this at massive scale with great effect for a number of use cases across different domains. And that's, again, something that Eric is going to touch on during his demo. So I won't say much about it, but you'll see more in the demo. We started with a platform that was TDA-centric, and where we are right now and what we are in the process of building and we are going through is to make sure to build a platform that really enables us to go to the next generation of what we are envisioning for our applications. So again, on the right, if you go from right to left, on the right, we have all of the different verticals and the applications and the different verticals that we are building the platform, or we're building the platform for. And then within the platform, as I mentioned, it is a platform meant for data scientists and citizen data scientists, so business experts. And the platform is really powered by the rich domain-specific data models. We enable the entire cycle from data exploration to inference. We have deep exploration and segmentation powered by TDA, and we have a rich library of domain-specific pre-trained models, if you will, that enables us to build these applications rapidly. All of this is enabled by our open data and ML pipeline. It is open, it is built on open source. It is open, which means you can bring your data, you can extend the platform with the models that you bring, with any of the tools that you want to integrate into the pipelines. So we've really built it to be as open as we possibly can, while having opinions about what the platform is, because it can be an infinitely open platform. And as I mentioned, it's built to scale, and we support use cases ranging from batch to real time. Next slide, please. So when we think about the different layers of the pipelines. So we start with, if you go from bottom to top, as I mentioned, we are cloud native. We support both all the public clouds and on-prem as well for customers that want us to operate on-prem or within their private cloud. And our data pipelines enable us to have all of the data connectors that we need, and we keep adding new data connectors as the need arises. And all of the data wrangling that we need to do, we support through the pipelines. And oh, by the way, we also have we support the feature stores for all of the features that the models need in terms of the ML pipeline. All of the normal capabilities that Sergio showed as well earlier are almost table stakes that we must support. And you'll see this in every data and ML pipeline. So these are core capabilities. All of the work we've done is based on Docker and Kubernetes. So that's what we use for our containers. And our ML engines, as I mentioned, we started with an engine or a platform that was TDA centric. And we still clearly support TDA. We've containerized TDA. But in addition to doing that, we also support all of the other open source ML libraries from Scikit to Tensor, Keras, Stats Model, and so on. The low code, no code framework is an interesting one because that enables a lot of the tools for both data scientists and citizen data scientists. Next slide, please. And I won't drain this because I do want to give Eric as much time as I can to do the demo because that is going to be much, much more interesting. But here's a really quick view of how we are building the components that go into building the platform. If you go from bottom to top, right to left, all of the capabilities that on the right, observability, DevOps, security, these are, again, core capabilities that every platform needs. From a data pipeline perspective, we are using Apache NiFi, Kafka as a data or streaming backbone, all of the data adapters, cleansing, transformation, null imputation for data wrangling. We're using fees for our feature store, Postgres for all of our metadata storage. And the ML pipelines are powered by Argo and MLflow. You can see what we're doing for optimization, inference, and all of the different libraries we support. And every layer and tier of the platform has both REST APIs and Python SDKs right now. All of our UI is built in React. The data science workflows are grounded in Jupyter. So our goal is to enable a data scientist to go from data exploration to inference and deployment, all from within a Jupyter notebook. And our low-code framework is the capability that enables us to build citizen data scientist or business expert applications that enables a business expert to leverage our ML models and features without having to be a data scientist. I saw some questions come by. And so we'll quickly answer that right after this. So this is just a very quick view of all the different customers that we have across the different industries. As you can see, it's a fairly broad and diverse base of customers across the different industries.
All right. Well, thank you, AJ, for that really great overview of SymphonyAI and EurekaAI platforms. I think, as you can see, it's quite capable platform. I think there are a lot of features and capabilities that are just really, really great to explore and see, how you can get started in applying to innovation use cases. I think we had some questions. Do we want to go ahead and take a couple questions before we proceed to the demos?
Sure. Let me actually take the first one, Vijay, if you don't mind. And I'll actually use an example from one of our real world customers, somebody who does leadership analytics for the top 1,000 companies. So they fill out surveys, they take evaluation reports, they get all kinds of demographic information on employees who are in leadership positions and employees that companies feel should possibly be promoted to senior leadership positions. Typically, what they've done is they've sort of sliced it and diced it in a very biased way. So they may break down people by gender, race, education, all those categorical variables that you and I would use as we were going to do that analysis, right? Because as they start to look at the analytics, there's not a lot of variation in the questions that people are answering. And so there's a weak signal there. And of course, most techniques, as you get really wide, may use something like dimensionality reduction or something like that. And so they're going to miss out on the weak signals because all that variance is in those early bias terms. So they really struggled with how to do their work. So we actually worked with them. We actually worked with their data scientists and actually took those biased demographic type terms out and only looked at the pure numbers that were coming from the survey, some of the NLP from the free structured text. And we built cohorts in the segmentation models like you see we're going to do here in a minute with medicine that enabled them to do it purely based on answers from the questions without race and gender and all those other things that could bias it. But then afterwards, after they found their cohorts, they can overlay that information to find out what those groups behave like. So they don't have to use that to do the segmentation, but after they do that based purely on the numbers, based purely on the responses that the survey people give, they can overlay that to inform their decisions. And so they've actually published a white paper about it. I can share that link with Sergio after the call and he can distribute that. But there's a really interesting use case story on how that's typically done with TDA.
Great. Thanks for that, Eric. I think the next question was how we improve our models when deployed across multiple segregated environments, and are we making use of federated learning? The short answer is yes, we do use federated learning. And when we deploy our models across these different environments, clearly we are working in a specific vertical for a specific customer, and what we strive and do as we work with our customers is to make sure that we are with the appropriate checks and balances in place to make sure that we are not passing any proprietary information or PII and those types of guardrails which are non-negotiable. The advantage that we provide to our customers is then being able to take some of the patterns, the learnings, and then be able to retrain our models, both as we identify, let's say, data drift, model drift, or specific use cases that the models or features need to be tuned for. And by doing that, all of the customers benefit. So we clearly have some guardrails, but there is a lot of advantages that our customers get as well from our ability to really enable and apply federated learning across our models for the different customers. A lot of the work we do in retail is a classic example of that.
All right, great. All right, so I think we're all ready to see some demos. So I'll let Eric take the stage.
All right, great. And just to check, you guys can see my screen, correct? Sergio, can you see my screen?
Yeah, I can see it.
Yeah, we can see it.
Okay.
Yeah, we can see it.
Great. Okay. So I'm going to spend a few minutes today showing you actually a couple different views into our platform. The first one that you see here is Workbench, and this is really intended for the data scientist or the data analyst who wants to explore a data set and build topological models quickly. So I'm going to dive into this first data set here. This is actually a data set based on a Norwegian breast cancer study. And I like to use this data set because it's not a toy data set. Obviously, toy data sets are easy for all models to use. This is a real data set. It was published about 20 years ago and really explored by a lot of statisticians and experts trying to find patterns within the genes for cancer patients. And so this data set actually consists of about 270 patients. And so here what we're looking at is the columns of the data and some metadata information on them. So whether they have nulls and what the distributions are, but these are actually gene expression levels. So all these funny names that you see here, they're just different genes within the cancer cells. And then the values are z-scored expression levels for those genes. Now there's two pieces of metadata in here. One is the patient ID, which obviously we wouldn't want to have in our model. And the other is event death, whether the patient had lived or died by the end of the study. So we could obviously build a supervised model here. We could obviously say, hey, build a model to predict event death, but that's not what we care about. We actually want to find the genes and subpopulations within the genes. So we're going to build an unsupervised topological model here. So what I've done is I've just highlighted all those genes, and I'm going to create a feature set. Those are going to be my independent variables, and I'm just going to call that genes. And you see that here now. So I've got 1,500 columns. You actually see, if we quickly look at the data, I've got 272 rows of patients. So here's a quick little data view showing those gene expressions for each patient. And I'm going to go build a topological model. And so I'm just going to hit create here. I have to fill in a few pieces of information. I'm going to go to that quickly because it's going to run for a few seconds. I want to explain what's going on while that's happening. I have to give it a prefix because it's actually going to look at about 12,000 possible parameters that can go into a topological model here, and it's going to find the ones that are automatically the highest scoring ones and just return those. So I'm going to give it a prefix. I'm going to choose all my source data. Now, if you had a predictive model you wanted to build and you had training, validation, and test data sets, you could obviously do that. But here in the unsupervised analysis, I'm going to choose the whole data set. And then I'm just going to choose the gene columns that we chose earlier. And I'm going to go create my topological models. Now you see it's running here. And I mentioned earlier that I had about 12,000 possible combinations. And those consist of metrics and lens values that we can choose here. I won't dive deep into what those are, but those are values that influence the topological model, as well as hyperparameters that go into that. So you can imagine if a data scientist had to figure out which of these 12,000 possible combinations they could use, that would take quite a long time. But as you saw, the AutoML features of the platform surface those very quickly. I'm just going to show you a couple different views that we see here with topological models. So changing the view around a little bit. So these are all just different slices of the data. None of them are right or they're all right. None of them are wrong, but some may be more helpful in certain situations. So I'm actually going to focus in on this one, and we're going to use this one as we explore what's going on here in topological model today. Now I'm going to briefly tell you what we see here on the screen, what a topological model is, and then we'll dive into how we use this to do some analysis. So you'll notice that here on the screen I've got 45 nodes, and those nodes are these points that we see here that make up the graph. And I've got a bunch of edges that connect those, or lines that connect those. And so those nodes and edges are what make up the topological model. Now you notice I mentioned I have 45 nodes, but 272 rows. So clearly a node isn't a single point, but it's actually a collection of highly similar patients in the data set. And so if I select this node right here, you see I have 6 patients there, and I can actually overlay the data, and we can see what those patients are as I select it. And I have 6 patients here in this node. Now, if I select both of those, you probably would think I would come up with 12 patients, but I'm actually going to select them, and you're going to see that I've only got 8 patients here. And so there's an overlap of patients that exist within the data. Patients can exist in more than one node. And an example I often give to people is people who are at a university, right? Some people may be students, some people may be professors, some could be both, right? I had grad students who taught me, and they were clearly in both groups. So here's an example of where that overlap between those two sets of people exist. So think of this as a Venn diagram on steroids. And when that overlap occurs, I draw a line between those nodes, and that's where the edge comes from. And those nodes and edges will give us the structure. Structure is what's important in topological data analysis. I don't care if this node's here or here. I don't care if it's singleton, which is an anomaly because he's not like anybody else, if he's here or here on the screen. What I care about is that I've got this main trunk, and right now it's colored by density, with a lot of patients who are very similar. But then I have these 2 flares that are branching off here at the end. So these are sort of 2 unique populations that I want to explore and see what's going on there. Now, I did this in a completely unsupervised fashion. I didn't use that event data to build the model, but I can overlay that to help inform now. So I can actually overlay by any of those features, any of the metadata columns, but I'm going to overlay that event death, that indicator, that 0 or 1, for whether the patient lived or died. And I'm going to color this topological model by that now instead of by density. Normally this is pretty fast. Oh, there we go. And so what we see here is a value of 0 means everybody in the node survived. And values that are higher than that, closer to a 1, mean that we had much higher chance of dying there. I'm actually going to just relax this a little bit, make it easier to see. And so what we see here is in this branch that we've got 100% survivability. So everybody in this branch, all 27 patients survived. But in this branch, the results are very mixed. Down here at the tip, we've got about 60% chance of dying. So only about a 40% chance of survival, but much higher probability, much better outcomes here at the base. And so what we want to do is we want to understand what's different about this branch across those 1,500 genes from this branch. And so we can do that by creating a group. So you saw me highlight these earlier. So I'm going to highlight that. And I'm going to call this the high survivability group. And then I'm going to create another group with this flare down here. And I'm going to call this one the low survivability group. And I want to understand what's going on, what's different between those. And so I could actually overlay a lot of these features in a visual representative way, try and figure that out, but that obviously doesn't scale. So I'm going to go down here and I'm going to create a comparison. And I'm just going to say, go compare my high survivability group to, I could compare them to the rest, but I want to know why they're different than the low survivability group and hit create comparison. So now what the platform is doing is going out and it's looking across those 27 patients and comparing them to the low population group across the 1,500 or so genes. And it's going to tell me what's driving that separation. What are those key factors that are influencing that? Sort of that explainability that Vijay and Sergio talked about earlier. And so what we see here is now we see a list of all the genes that are in the patients and how statistically significant they are between the populations. And we can start to click on them and we see we've got some very different distributions among these two populations. Now, what I want to focus on here is this ESR1 gene, and we see it's very different here between these two populations. This is actually something that's known in the field, so it's good that the platform is showing this. This is actually the estrogen receptor gene. And so actually, I'm going to overlay that topological model now, and I'm going to go ahead and color by that ESR1 now. And so what we'll see is not only am I able to see that in the table form, I can see that in the distribution that it gives me, but I can overlay and color that now and get an indicator of how that varies across the populations, because that's a gene that the SME would care about. Now I'm going to drop this down here as well, and I'm going to have that event death there. And so what we see is that the patients who had 100% survivability have very high levels of this estrogen receptor gene, and patients that are down here with the mixed survivability rates have very low levels. And I mentioned this was known in the field. And so what happens when they test your cancers, they find these biomarkers. They actually give the people who are in this branch the full gamut of treatment, radiation, chemotherapy, all of that. And it actually can be very debilitating for them. And actually what we find is that the people who are in the base of this don't necessarily need that like the people who are in the tip do. So what I can do is I can repeat that analysis, and I'm not going to do that because I want to show you a few other things, and I've only got a few minutes. But I could highlight this group, and I could highlight this group, and I could find out what's different between the high survivability patients in this flare and the low survivability patients in this flare, and understand those drivers and find biomarkers so that I can develop medicines for them. And this has been published in several papers, and so you can go read about this afterwards. And this is actually, we're doing similar work like this with the VA right now, where we're looking at COVID patients and doing subpopulations across 2 million patients. And within those subpopulations, we'll build local predictive models, but also determine optimal care paths because they're going to have all the medical interventions that were done for them. So not care paths that are optimal for everybody, but care paths that are optimal for each subpopulation within the data set. Now, let me pause there. I'm not monitoring the chat. Does anybody have a question on what I've showed you so far before I move into another view of the platform? No questions? Okay, great. So the next thing I want to show you is actually, I'm going to move from unsupervised to a supervised model, and I'm going to move from healthcare into the retail space. And this is a problem where it's a challenging problem where you're trying to predict how new items will sell in new stores, right? So when you have a new item, you're going to put it in a few stores. You maybe have stores across the country, and you need to develop a predictive model for that and understand how they're going to sell. And of course, the problem is if you develop a poor predictive model, you're going to make poor decisions, and that's going to lead to a poor sales forecast. Now, the data in this data set are store attributes, product attributes, and point of sales histories. But remember, these are new products, so it'll just be point of sales in just a few stores. And so what we're going to do is we're going to do unsupervised similarity using topology, like what you saw me do with the segmentation. And I'm going to build TDA embedding, so it features based on TDA that take advantage of some mathematical properties of TDA, specifically coordinate invariance and deformation invariance, that make it much less susceptible to small perturbations of the noise. So what it will do is it will tell me which stores are very similar to each other, which products are very similar to each other, and how are they very similar across the entire space. And then I can use those in a predictive model. And I'm going to show you that in just a minute. And you'll see here the results, spoiler alert, we actually got a prediction accuracy in the real data set of 92%, a 31% increase over the baseline model. Now, I can't show you the real data, but I'm going to show you some example data that we did. Let me make this a little bit bigger for the people to prove out the results. And what I also wanted to show you is how our data scientists may use this in a problem where they don't need to do a visual exploration of the data. They can do all that stuff I just did visually with just a few lines of code. And so what they did is they uploaded a couple sources here, those data sets I told you about. And then remember how I did that AutoML where I built those topological models? Well, I do that here in one line of code. I say, go do your unsupervised analysis on my features where I created my features there. And then, you saw me do some grouping, but I can actually tell the platform to do that. And I can use several different algorithms, but it will look across all the topological models and automatically group all the subpopulations for me. And then I do a transformation, which is really a similarity distance. How similar are the different populations that exist here? So for each row in each topological model, I'll say, what's the probability or likelihood you're in this segment versus this segment versus this segment? And I'll do it across all the topological models that I build, and I'll append those to my data set in what we call TDA embeddings, just like embeddings for word embeddings or other models that you may use. Now, the data set gets much wider, so I won't scroll all the way across, but here's the initial data set. And then as we go to the data set with all the TDA embeddings, you can see it gets really wide. I've got way more features here. It just takes forever to scroll across. And I feed that information into a model. So we can build the baseline model and then the TDA embedding model, and I'll do a side-by-side comparison here. And what we see is this is the actual score versus the predicted score for each one. A perfect model, everything would fall on the red line. Clearly, I've got some variation. I've got variation in both models, but we see we're a little bit tighter here. We don't have as much spread in the TDA embedded model as we do here in the baseline model. And what we can do is we can go down here and look at the final results. And what we see is in the R squared value, we get almost a 13% improvement in R squared. And of course, because it's a regression type model, we typically are going to use an error there. And you see we get almost a 15% reduction in the error of the model. So just a quick example on how we did this on a small data set. And we often do this, for instance, with one of the world's largest hard drive manufacturers. So they come to us with problems. They've got complex data sets. They've built predictive models over the last 6 months or a year. They can't get to where they need to in terms of accuracy to put it into production. And we use TDA in conjunction with their supervised models to build predictive models that score better, often seeing anywhere from about a 15 to 25% improvement in the error. There, I think we went from an error of about 5 in the units there down to about 3. So really big error reduction for them. And they were able to put that into production. Now, that's obviously, I didn't want to spend a lot of time on code, but I wanted to show you how our data scientists would use this in a notebook. VJ talked about notebooks earlier. And then we also have the citizen data scientist tool. So I understand TDA, our data scientists understand TDA. We can, data scientists may know the entire pipeline, but there are lots of SMEs and data experts who don't necessarily understand that pipeline and need help and want to take advantage of all those AutoML features that we have. So to save time, I'm not going to walk you through how to do this, but one of those SMEs can go through a guided UI in about 10 minutes and develop these predictive models. So I did this earlier on a diabetes data set. I'm going to jump in here. Normally what you do is you'd say create it, you'd give it a few pieces of information like I want to predict disease in patients. You upload your data set and you just answer a few questions. So it'll drop you into this page here and you say, hey, what am I trying to predict? And I can do unsupervised analysis here and anomaly detection and all kinds of things. But this is a predictive model. I want to predict disease in patients. You deselect the metadata columns, like that event depth we talked about. Obviously, I deselect the answer. And here I've just gotten rid of a row ID. That's not very important. Now to help out, we can build some models here, some graphs. You guys know how to build graphs, so I'm not going to spend much time on that. And then you would just click, accept this data, and it takes you to Workspace. You click a blue button, and it goes through and it does feature generations. It cleans everything up for you. It does one-hot encoding on the strings. It does symmetric log scaling on numeric features. If you happen to have nulls in the data, this data set was very clean and didn't, it will do null imputation for you. So it will do all that for you automatically. Then it does feature selection. It looks at the original features and choose a subset of features that give you the best signal to the target, as well as the expanded feature set on all the ones that it did. And so then it builds 10 topological models, 5 for each feature set. So I'll just look at this one here quickly. We see a topological model set of these diabetes patients. And you see I've got some various subpopulations here, and it's already done the grouping for me. I can click on a group and it'll highlight them here on the model. It's hard to see because it's blue. Let me click this one. So you see that's the group right there. And now when I'm on this blue model here, I can go down here and I see the data that exists in the model in that subpopulations. I can change what I color by here, just like in Workbench. And I can go look at the group insights. It's showing me what are the explainers for this group. Why is it different? How big is it compared to the other groups in the population? As well as what are the significant features that make this population different from the others? And it did this all, and it does this all in about 5 minutes. Plus it builds predictive models. And so this is a classification model. I'm trying to predict whether you're type 1, type 2, or no disease diabetic. And obviously this one is scored pretty well, but it gives us some random forest models, some logistic regression models, some decision tree models. Let me click on this one. It's not a perfect score, so it'll be great. And so what it did is it took the data that we uploaded, it did an 80-20 split on it, a train test split. And this is the results on the out of sample data, that 20% that it hadn't seen. And of course, as I'm going through here, I can actually pin these to the dashboard, which, just right here, I can say pin or unpin something. And so I've got a nice summary now. I don't have to go through all those things where I've got maybe some of the charts I wanted to see. I put in a note there. What is my predictive model? And what's my topological model? And now this is actually a deployed endpoint. You can start to do predictions now. And all you have to do that is you have to go here and you just say add a test data set. And I already did that. And so this is data that it's never seen before, and you can choose which model you want to run it on. And so I ran it on this one. And so this is what the model looked like originally. This is obviously a different one than I picked over there to just show you. But the 80%, 20% split that it did. But then here's out of sample data that it did, how well it scored, and you can download the predictions for that instantly. And that's a deploy point that an enterprise engineer or somebody can start hitting as part of a REST API, as part of a solution to feed a dashboard, etc. So I went a couple minutes over. I tried to get through that quickly, but there's a lot to cover in about 15 minutes. I think when Sergio and I did this the first time, we spent about 90 minutes going through this stuff. So hopefully it gave you an idea of what TDA is, how you can use that to solve supervised and unsupervised problems. And let me pause now and see if anybody has any questions.
Yeah, Rick, thank you for these demos, these amazing demos that I think we've seen quite a bit in a really short period of time. So I think we'll just jump right into any questions that people may have. Let's see what I think there was a question about availability and pricing. Jay, do you want to, or Eric, anybody want to take that one?
Sure. So one of the things that we've done is we've said that after this, we'll make the platform available to some users, so you can start to see if this makes sense for a data set, to see if TDA can help you solve the problem. We can provide some training classes to you. And so what we'll do is there's a couple training classes. We want to schedule that to maybe get as many of you into them as possible. And we can record them and then make them available to you offline. So you guys can actually, bring a toy data set. We can go through the training analysis. Actually, I'll bring toy data sets. We'll go through training analysis, show you the buttons, talk about some of the math behind this in a couple-hour classes, and then you can go off and play with that on your own. So Sergio, I'll work out the details afterwards, but if we can get a list of people, we'll stand this up and make it available to you. It's a SaaS instance. You just access it from a browser. It runs on AWS. So
great. There's another question. Are you also planning to make use of neural network deep learning, and for what use cases?
Excellent question. Let me take that. One, we actually have some deep learning neural nets capability in the platform now, and that's where we actually do. We build ensemble models, whether we're doing embeddings or model stacking and other things like that with TDA. I showed you a random forest, logistic regression, decision trees. One of the options there is a neural net. And we do some neural nets also in our algorithm scoring to tell you which topological models are the best. But in the 4.0 platform that VJ talked about, that's going to be part of that platform with TensorFlow and other things like that there. So you can use that as well on the platform. Now, you talked about a use case. There's actually a great use case where TDA is actually used in conjunction with neural nets. And I talked earlier about some of those mathematical properties that make it much less susceptible to noise. And so what you do is you can obviously use a neural net to build, convolutional neural net to do image classification, and that works great in the lab. It works great on your data set. When you put that out on the real world floor, we often get a sharp drop off in the accuracy of the model due to just that variation in the underlying data. And there's been a lot of academic papers written on subjecting the results to Gaussian-based noise and random noise and things like that, and how the neural nets drop off much less dramatically when they're used in conjunction with TDA and we build those embeddings. So there's one example right there.
We have another really, really great question. Eric, I think we've talked about this one before. How does SymphonyAI make sure its platform produces rational, explainable, intelligible decisions and are not based in their design, training, or operation? How do you limit risk and improve the fairness of your AI ML systems?
So I tried to address that a little bit earlier with that bias question, but let's talk about how we get reasonable results, right? How do we know, for instance, in that medical model that we talked about earlier where I looked at those segments, how do I know that those make sense? Well, I don't know what any of the columns mean, right? So we work with the SMEs, we work with you, we work with the people in the field, and we say, hey, we had about 12,000 possible topological models. These are the top 5 or 6 from the platform. Here's subpopulations that I'm finding. Here are the key drivers in those subpopulations. Does that make sense? And the SME will come back and say, yes, that makes sense, or no, it doesn't. If it doesn't make sense, then we maybe need to iterate. We need to do some feature engineering. Maybe we need to do some feature selection and get rid of some features. Remember, we often do this with data sets that are not 10s, 20s, or hundreds of columns wide, but thousands, tens of thousands, or even hundreds of thousands of columns wide. Probably the widest data set I've ever used in reality is about 500,000 columns, sorry. But obviously, I may come up with some models that don't make sense. And that does happen. Our data scientists come up with a groups or a model. We go to the SMEs and they say, no, those models don't really make sense, especially in a completely unsupervised analysis. There's no type of target. There's no semi-supervised analysis that's done. It's really finding subpopulations and working with the SMEs to make sure that it makes sense. And that's the way we typically do that.
Great. Yeah, and I know we mentioned availability of some training materials, and Eric and I will be working to get a set, and we've already started putting some stuff together, and we will be sharing that information on those resources for anyone who might be interested, and we'll be sharing that so that you can start diving right into the platform and getting access to be able to do things like some of the things you saw Eric do with the TDA demos, which I think are really interesting to kind of get your hands on and see how you can achieve a really dramatic acceleration in how you apply machine learning pipelines to different use cases and problem sets. Any other questions? I think we have just a couple minutes here left.
I see one in the board that talks about skewed data, and we actually often use TDA as a data exploration tool to look for bad data, skewed data, things like that. There are some techniques in the platform to handle that, but often what happens is they sort of pop out as their own, population. Maybe you got a right-tailed skew thing, right? The classic example is everybody's salary and Bill Gates and Elon Musk are way out there to the right. What happens in TDA is we're looking for people that for similarities. And that skewed data is an anomaly, and it's going to pop out as a singleton. It's just going to be one of the side effects that come out of TDA. So we often just throw the data into the platform, and TDA says, here's data that makes sense. Here's data that's like everything else. And then here, are things that are anomalies, that are outliers. One example that we use in a current customer that we have is in the cyber threat domain. Everybody knows how to find threats you're already aware about when you detect patterns, and that's the way traditional techniques are done. But what about zero-day attacks, new threat vectors? How do you find those? And they actually use TDA on their Splunk logs before it ever goes into supervised models to find those anomalies and those new threat vectors And so, there's an example of some data that's, very unique and different. It's different from everybody else. It pops out as an anomaly. But usually those just surface as different subpopulations or segments or anomalies within the topological model. There are some things we can do in the hyperparameters to bring that skewness in if we're not looking for anomalies and we want to do some stuff. But it really depends on the problem and the data, just like every data science problem.
And I'll quickly add, as we are thinking about the data pipelines in the 4.0 platform, detecting and flagging biases in the data. If the data is too skewed based on certain patterns, is something that we will be flagging. So we are evaluating a few different techniques, including obviously using TDA to help us flag it, but that is going to be part of the platform.
All right, great. Well, thank you everyone for joining today. I hope you learned a lot and taken away something that you can start applying for your, innovation for products and services in the enterprise. Thanks to Vijay and Eric for joining us from SymphonyAI. And we, like I said, we will be following up with some resources that you can get access to and start, looking into the platform and seeing how you might be able to apply it for your innovation projects. So thank you all.
Great. Thank you.
Thank you, everyone.